Dr. B. Venkateshwaran was born in, he obtained BSc MTech and PhD degree in Advanced Materials from the University of Malaya, Malaysia. He joined NanoCat University, Malaya in 2005 since 2007 and Senior Research Officer in Center for Ionics, University of Malaya, Faculty of Science, University of Malaya. He has joined Power Energy Dedicated Advanced Center in the year 2017 as Senior Research Officer with grade Q52. He has published more than 40 research papers in high-ranked journals. Dr. B. Venkateshwaran sir is the Research Director for Advanced Materials Science Laboratory in Institute of Postgraduate Studies and Research in University of Malaya. He is also a research consultant for Dakin Malaysia, SDN PhD, and also for Shivafi Dental Products. He has been successful in securing substantial funds for research as co-researchers from University of Malaysia and Malaysian government funding agencies industrial grant from Daikin Malaysia. He has got one Malaysia patent filled for his credit. He is also a senior member in leading professional associations. He has received several awards and medals in participating International Technological Expo, including ITEX, MTE, PECIPTA, and Bio Malaysia. He won the best of the best in electrical and electronics category at PECIPTA 2013. Recently, he won the best award in MTE 2016 and MTE 2019 with the gold medals. He has involved in organizing international conference and participated as panel of judges in National Science Fair for Children. He has presented many research papers in international conferences. He has just won commercialization grant and bringing self-cleaning coating product for commercialization with University of Malaya. Thank you so much, sir, for this occasional awards. Now I hand over the session to our resource person to start the program.
Okay, thank you so much. Thank you so much for the nice introduction. And thank you so much for giving me an opportunity, Dr. Krishnaveni, and the principal of Idhaya College of Women. And I would I would like to share my screen now. Okay. Okay. So everyone can see the screen?
Yes, sir. It is visible, sir.
Yeah, it's a similar screen, similar presentation of mine, which I have already sent before. So can we start now?
Yes, sir.
Okay, right. Okay. Good afternoon to everyone. Okay, before I go into the topic of discussion today, okay, before I start with my presentation, a little bit introduction of in Malaysia, where we are located. Okay, so actually I'm located, the university which are located is the University of Malaya, one of the first university and a prime university in Malaysia. Okay, and one of the oldest university as well in Malaysia. Okay, and I'm situated in a building, we call it as Wisma R&D. Wisma R&D means Research and Development Wisma of University of Malaya. And it is about 6 minutes drive from one of the LRT station, light railway transit station in KL, in Kuala Lumpur. Okay, so now, these are the awards which our Center of Research has already obtained from 2008 until 2018 for past 10 years, and many more, which I never included in the slides. Okay, And the person who is over here, this is our director, research director. Okay, our research director is Professor Dr. Ayar Nasaruddin. Okay, and over here, this is our research focus area mainly. So we are in University Malaya Power Energy Dedicated Research Center, where we do smart grid system, okay, EV, what we call electric vehicle, EV vehicle research center as well. And also we are into solar energy research center as well, okay. And we are also into PCM, that is phase changing materials for solar panels, okay. So this is our key research areas which we are covering in our research center. And this is our core businesses, okay. Our core businesses is our research activities, okay. We focus on research activities, international conferences. We are not only doing research, we are also patent our research and also bring out prototypes and products. And in that sense, we have few products which we have already come out. And one of it is our self-cleaning glass coating, okay. And apart from that, we also come out with our own inverters as well, okay, for solar panels, okay. And we have gone into high impact publication. We are collaborated with industry collaborations as well. Okay, so this is our HICO Research and Innovation Core. This is our main objectives of our key performance indicators, which we need to do over here. Where over here, we are more focused on quantity and quality of researchers, quantity and quality of research, quantity and quality of postgraduates, and networking and linkages and resources as well. Okay. So this is some of our research facilities where we have our own solar farms, we have our own solar garden, and we do also stimulation research on all the solar panels as well. Okay. So this is our own postgraduate students, we also supervise postgraduate students and also graduate students and also master's students as well. Okay, this is our research products which we have already obtained, which we have already got it. Okay, so this is our solar kiosk. Okay, our own solar kiosk with it is can be self-lightable by itself by using just a solar panel. Our solar fountain and garden lighting systems in our own farm, and this is our greenhouse of photovoltaic PVT concept and solar street light systems, which we have already set up in our department itself. Okay. So this is our research products, which we have already gone into, bring it into market. Okay, these are the research products. Okay, so these are the industry collaborators we have and all the grants we have listed there. So one of that is PESTEC Discovery, prestigious Discoveries Number Hat, MS Elevators. Tenaga Nasional is our national electric board company. OIL is one of the aircon manufacturing company, and TNB is our electric board research centers. Okay, we have collaborated with them as well. Okay, so these are our linkages with all the universities internationally and also locally. Okay, so these are our collaborators with other universities as well, and we are open for collaborations. Okay, now I'll go into the topic today. So the topic of my topic is self-cleaning industrial coating. Okay, my name is Dr. Venkateshwaran from University Malaya Power Energy Dedicated Advanced Center, Institute of Advanced Studies, University of Malaya, Kuala Lumpur, Malaysia. Okay, so now here we are going into why we come out with this technology or why we come out with these coating systems, because of that is why the introduction comes in with problem statement, objective, and experimental. Then we go into results and discussion and the ideas and the future works which we are going to perform. So first of all, when we are talking about dust and dirt on glass surface, this is not only on solar panels, okay? Because when a dust is accumulated on a solar panel, it will reduce the efficiency of a solar panel, okay? Apart from the solar panel, we can talk about high-rise buildings. When we are talking about high-rise building, these high-rise buildings, they have what we call a problem of cleaning a high-rise building with glass panels on top, where number one, either they have to use a gondola or they have to use a Spider-Man method to do the cleaning, which is, one is very costly, time-consuming, high amount of energy consuming, and very risky job. So that is why we came out with a coating system where it can do a self-cleaning by itself, okay? So in a practical way, the glass can be coated with a hydrophilic self-cleaning coating system in order to expel dust particles via action of water droplets. Either it can roll off or wet through, or it is what we call sliding off, okay? So the hydrophobic surface can rolling off or sliding the dust particle away, whereas hydrophobic particles will remove what we call hydrophilic surfaces, will wet the surface and bring down the dust particle down, okay? Okay. So next. So our problem statement, most of the problem statement is, most of the research studies have developed self-cleaning coating. However, the process are too complicated, time-consuming, requires a specific equipment and machines, and can be applied only on small glass substrate, not on a bigger piece of panels. Okay. So over here, the research conduct their self-cleaning tests in lab environment only. Hence, the self-cleaning performance against outdoor environment still doubtful. So, several self-cleaning coatings systems exhibit low transparency in UV visible region and seem impractical for photovoltaic and window glass. Okay. Okay. Next. So our main objective is to find a novel self-cleaning hydrophobic coating that can be spray coated on a large glass scale, easy synthesis process, and can be cured at room temperature. We doesn't want any oven curing process over here. So there is no oven curing process. It can be cured at room temperature at ambient condition. Okay, number one. Number two, to synthesize a transparent self-cleaning organic coating with the best blending ratio on the glass substrate, and to improve the self-cleaning ability and the hydrophobicity and anti-fog property by adding nano calcium carbonate particles into the best blended binder system. Okay, because when we are talking about a coating system must consist of fillers, that is nano calcium carbonate, and also binders. Binders is the one which is binding the nanofillers with the glass substrate, on the glass substrate. Okay, so we need to identify what is the binder is useful, or it can bind with glass substrate. Okay, because photovoltaic panel on top is a glass substrate, or building glasses we have only glass materials. So another thing is to discover the durable composition of organic binder system that can strongly adhere the nano calcium carbonate onto the glass substrate, because we need to have a proper binder system that can adhere the nano calcium carbonate. That means it can hold the nano calcium carbonate onto the glass substrate and also inside the within the coating system. Okay, so that is the reason. So ours, we use a very simple synthesis method where our raw materials we use is PDMS and Silgat. We mix together at 50 degrees Celsius. PDMS and Silgat resin was diluted with ethanol, okay? And we stir it while using a normal stirrer without any kind of heating effect. There is no heating, okay? Apart from that, okay? After that, we do a deep coating on the glass slide, or we can do a spray coating method. Deep coating for small glass substrates like glass slides and all that, or for large glass plates, we use spray coating method and we leave it dry at the room temperature and it dry within 10 to 15 minutes, okay, at ambient condition. So this is our formulations of our PDMS and Silgat, where the Silgat, we use it as our, what we call, we increase the PDMS, the Silgat value, the weight ratio of the Silgat we increase, but the compatibility ratio of the PDMS, we fix the PDMS ratio, but we increase the Silgat and we find what is the best property out of it, okay? So after that, after we do the coating system, okay, the PDMS Silgat system, we are doing water contact angle measurement to see how is the hydrophobicity of the material, of the coating system, to see the cross-linking ability by using Fourier transform infrared spectroscopy. Okay, mechanical properties, anti-fog properties, and outdoor self-cleaning tests as well. Okay, next. Once we get the best blending ratio of PDMS and Silgat, we introduce a nano calcium carbonate into that system and we do the same characterization. But now we are going into FESEM to see how the dispersion of the nano calcium carbonate on the substrate, FTR spectroscopy to see what is the cross-linking ability, and water contact angle basically to see whether it is becoming more hydrophobic or become less hydrophobic, or the hydrophobicity is declining or is increasing. Okay. Apart from that, we do X-ray diffraction analysis to see how the calcium carbonate is been bonded, whether it is on the surface or it is inside the coating system. Okay. And then we want to see the mechanical properties. We see the anti-fogging properties and outdoor self-cleaning testing as well. Okay. So these are the tests which we carried out. So now for binder system with PDMS and Silgat, okay, once we are increasing the Silgat ratio with the PDMS into the PDMS, okay, the bare glass, you can see the contact angle is about 59. I would say about 60 degrees. Okay, the contact angle is about 60 degrees. The water contact angle measurement is 60 degrees. Okay, when we are introducing the coating system with PDMS and Silgat together, okay, okay, now when we are introducing the Silgat into the PDMS coating system, the water contact angle tends to increase and the hydrophobicity tends to increase. So as the Silgat ratio is increasing from S1 to S2, okay, the contact angle increases, then it starts to decrease back. That means it goes up and comes down. And why? That is due to the what we call cross-linking ratios. We would say that the PDMS Silgat coating improves the water contact angle of bare glass above 90 degrees. PDMS Silgat resin consists of non-polar methyl groups like CH3 and interface that have minimum interaction level with the water droplet, and higher content of Silgat improves the water contact angle of S2 containing as high as 103 degrees. However, excessive Silgat reduces the water contact angle because the system becomes more hybrid network of SiOH, silicon hydroxide methyl group chain. So this hybrid network causes the decrease in silicon carbide chain length, which leaving behind unreacted long alkyl chain. So the unreacted long alkyl chain lead to the decrease in the hydrophobicity of S3 and S4 coated substrate when the Silgard value increases. And this we have already published. Okay, so this is the EDX which we have done on the binder system alone, where you can see that the when the value of Silgard is increasing, okay, when the Silgard weight ratio is increasing, the carbon content is increasing. Then it starts to decrease because the cross-linking is taking place higher cross-linking, and the carbon ratio becomes lesser. This is another evidence to it. So this is Fourier transform infrared spectroscopy. Over here, the pristine PDMS, the pristine of PDMS represent FTR peak of CH3 stretching, SiO, Si stretching, and SiCH bending. And the OH peak in PDMS Silgard is excrete with vibration of hydrogen bond ethanol molecules. So Silgard contains C double bond C double bonds on their structure that is possible to chemically react them to the polymer of PDMS matrix. So C double bond C stretching at 1650 Cm-1 decreases in intensity with increase in Silgard content, because the CH double bond CH chain in Silgard intermediate has reacted with silanol group in PDMS. So the SiO, Si splits separated bands at 1020 Cm-1 at the wavelength of 1020 centimeter and 1090 centimeter, indicating formation of hybrid coating structure where the functionalization of sinolor's linkage through silicon breaches by methyl groups. The silicon carbon bending mode decreases with increasing Silgard content because hydrocarbon parts of the PDMS Silgard molecules starts to get in between the ethanol molecules. They break the relative strong hydrogen bonds between ethanol molecules within or without replacing by anything good, and this makes the process energetically less profitable and so soluble, so the solubility decreases. So this is why the hydrophobicity decreases over here. Okay. So now this is the reason when we are going above, when the PDMS is increasing over here. This is the PDMS. This axis shows, the x-axis shows the PDMS and the y-axis shows the solvent. So when we see the Silgard, okay, when the Silgard increases by the weight percentage from 5 weight percentage to 20 weight percentage, the reaction on the 5 weight percentage, a low reaction of PDMS is taken place. Ideal is a 10 weight percentage of Silgard over here, and above that is the high reaction of PDMS with Silgard increases the cross-linking density, I would say. Okay. Apart from that, we have to see any coating means we have to see what is the mechanical stability of the coating. So we do a scratch coating, scratch test by using one of our instrument over here for micro scratch hardness test we use, and that is one of a very important test in coating industry. Okay, for coating industry as well. So now, when we scratch, we can see that as a transverse cracking is taking place, partial ring cracks tensile crack, delamination takes place over here, and total failure takes place over here. So from here to here, the weight, the force which we apply on the needle, it will increase when it goes up further. Okay. So from here, with 4 Newton, the force with 4 Newton, we get the failure point in S1. But the failure point in S2 is resulted. You can see the failure point in S1 and S2. But in S3, there is no failure is observed with 4 Newton. And the failure point again observed in S4 at high dense cross-linking density, which turns to be more brittle. The coating tends to be more brittle. The organic coating become more brittle due to higher cross-linking densities. Okay. So from here, we can say that, we can conclude that the PDMS Silgat coating exhibit elastic and stiff property that resists the deformation of the coated substrate at lower applied load. The cross-linking density significantly alter the tensile stress strain behind behavior of the resins. Higher degree of silicon oxide silicon cross-linking in elastomers restrict the ability of chain to unconditional and raises the stiffness of the coating. Okay. Next, the higher number of cross-linking in PDMS would create more identical terminating methyl groups that act as a binder. Because when the cross-linking of, when the Silgat, which has been introduced in the PDMS becomes higher, it creates more identical terminating methyl group that act as a binder. So low degree of cross-linking construct less rigid, what we call less rigid coating system that obtains slightly lower hardness, and S3 coatings has higher hardness coating. Strong SiO cross-linking delays the cracks of propagation and initial fracture behavior. The S4 coating has a slight lower hardness because of saturated cross-linking density, build a hard and brittle self-linking brittle silicon resin network during curing process, and silicon resin network, and the structure determines the effect. Okay, and this is why when the cross-linking becomes higher, the hardness becomes lower. That means it becomes more brittle. It built a hard and brittle silicon resin network during the curing process, and it fails and becomes brittle coating. So this is Vickers hardness. We have done Vickers hardness as well. Okay, and you can see from there the S3 coating system is the one which has the highest hardness of gigapascal 9.81. Okay, so this shows that this corresponds exactly with what the mechanical, the cross scratch test which has been seen. This is the anti-fog property. So for the anti-fog property, what we did is we take our glass substrate, which has been what we call coated with our coating system, and we put it on a hot water, vapor of the hot water, and we leave it over there to evaporation of the water vapors. So this is the time taken, the evaporation time taken for it to evaporate. Okay, so the anti-fog performance of the bag glass of the coating, the bag glass and PDMS coating systems with about at 130 degrees Celsius, okay, above a hot boiling point. Okay, so we can see the evaporation time, okay, of the coatings. It varies. So that means why the evaporation is very fast, because due to the hydrophobic properties. Because from here the bag glass is 25 minutes, now it becomes 10 minutes. It's more to half, and this is due to the hydrophobicity of the coating system. Okay. So this is what has been cleared over here. Okay. The bare glass substrate possesses a blurry image due to the addition of large droplet. The large droplet condenses immediately on glass surface, then scattered the incident light. So all the PDMS Silgat coated have displayed clear images because the coated glass were adhered by tiny mist droplet only. Okay. So the S2 and S3 coating, the fastest evaporation time among the PDMS Silgat coated surface, and this possesses higher amount of non-polar methyl group SiCH3 at the interface. Okay, this corresponds to high amount of methyl group give stronger repulsion to the polar fog droplets and inhibits the nucleations of growth of fog droplets. So the S4 coating shows the longest evaporation rate because of saturated SiO-Si linkage at the interface, a strong attraction to the fog droplets. These are the tests has been carried out, standard test of VS-EN 168, where the S2, S3 coating can maintain its anti-fog performance, while the S1 and the S4 is due to the large droplets. Okay, coating with adhered with the large fog droplets. Okay, so this is how we can see it over here with the anti-fog performance with the BS-EN 168 with standard testing methods. Okay, so from here we can see that the S2 has 12 minutes. It's much about 50% lower than the S1 other coating systems, S1 and S4. So this we have choose the S2 is the best coating binder system, and now we introduce calcium carbonate into it, and we see the water contact angle measurements. So we are seeing the water contact angle measurements. When we introduce the calcium, nano calcium carbonate into it, the water contact angle tend to increase. Okay, so that means the hydrophobicity tends to increase further. Okay, so with 0.4 weight percent of nano calcium carbonate into it, the hydrophobicity is increased to 107. The contact angle increases to 107, and when with 0.6 weight ratio, it increases to 108, and for with 0.8 weight percent, it increased to 110. But after that, it shows a decrease. Okay, and this is due to the agglomeration of nano calcium carbonate on the surface. Okay, this is what happens when we put nano calcium carbonate particle on top of the resin. Okay, on your right, you can see that a smooth A1 coating system. The A1 coating system recorded less water contact angle than S2, indicating that the possible interaction between a hydroxyl and a silicon resin and the polar waters. Okay, the presence of the residual oxygen containing of group of SiOH group in uptest causes the water to absorb and tightly bond to the surface. Embedded when it is embedded with calcium, nano calcium carbonate, it forms like a cushion over there, which it repels the water droplets. Okay, so it reduces the contact angle between the coating and the water droplet. Okay, so the higher weight percent of nano calcium carbonate can achieve water contact angle as high as 110 due to the formation of air pockets that suspended the water droplets and becomes more hydrophobic. Okay, and the water contact angle at A1 and nano calcium carbonate coatings system C5 and C6 reduces or lower because of agglomeration of nano calcium carbonate have narrow space, which causes low surface roughness. So with the weight percentage of nano calcium carbonate at 0.8 weight percentage, it shows ideal, the maximum air pockets it can make it. Okay, Beyond that, when we increase the nanocalcium carbonate, what will happen? Agglomeration will tend to happen, and this agglomeration on the surface makes the narrow surfaces and reduces the surface roughness. This is the FESEM diagram of what we have already got it. So with above the C5 and C6 coating, you can see that it is very clear that agglomeration is taking place and larger particles has been formed. Okay. So over here, the well-distributed coating system is C3 and C4. We can see that very clearly. So this is for FTIR. Okay. For FTIR coating systems, okay. Over here, okay, the FTIR spectra, this is for the S2 coating system and the A1 coating systems. Okay. This is with uptest, this is without uptest. So it's roughly the same. Okay. And now, when we increase, what will happen here is with the S2 chain and the uptest, we are using the uptest over here, okay, in order to cross-link, the SI-OSI bond with the binder resin, okay, over here, okay, and this is how the bonding is taking place over here, okay, and almost similar FTIR peak with A1 coating because low reaction with uptest, but the peak shift in FTIR spectra with various weight percentage of calcium carbonate confirming the reaction of calcium carbonate and uptest in A1 matrix. Okay. So this is the FTIR band ratios. Sorry. This is the FTIR band ratios which we have studied, where the peak shift has been taken place at all these peaks over here. So this is for X-ray diffraction. We can see that when the nanocalcium carbonate increases, the morphological factor from amorphous is becoming more crystallized. Okay, so the crystallinity increases. You can see at 111 and at 200 and at 112 over here. So it becomes a sharp peak is appearing. It shows that the crystallinity is increases due to the nanocalcium carbonate, which has been incorporated inside the coating system, into the binder system. So from here, we can say that the A1 coating system exhibits the amorphous phase at the broad peaks, and the incorporation of nanocalcium carbonate enhances the diffraction peaks of the coating system, and the reflection of HKL and 2 theta value of calcium carbonate is refers to our standard of the JCPDS number. Okay. So now, over here, the low diffraction peak at C1 and C2 coating system is inferred due to the dispersion of nanocalcium carbonate in the polymer matrix. And the XRD peak increases when the concentration of nanocalcium carbonate increases because of nanocalcium carbonate particles construct more polymerization sites, then creates number of crystallites. Okay. So the C6 coating shows the sharpest crystalline peak at 29.63. 2 theta angle of 29.63, indicating a strong formation of calcite phase. And the prepared resins from supersaturated of nanocalcium carbonate due to the absence of the scale inhibitors. That is over here, the C6 over here. You can see the sharp peaks over here due to the formation of nanocalcite of calcium carbonate, the nanocalcium carbonate. Okay. So this is the XRD peaks of A1 with nanocalcium carbonate coating systems. Okay, over here, where we can see the sharp peaks tends to increase. Okay, the 2 theta value sharps to increase over here, and from here we can see that the sharp peaks start to be observed at C3, C4, C5, C6 coating. And over here, the sharp peaks is due to the crystalline at 111 due to aragonite calcite. In C4, we can see more stronger peak of calcite and aragonocalcite. And the others in C5 and C6, we see the strongest peak at 29.36 and 36.28. The same thing goes at for C6 due to calcites. Okay, this is published. Now we have to see the same coating system with for the mechanical ability. Okay, now with only A1 coating, it forms a elastic coating materials over here. Okay, and okay, so here we see a soft with calcium carbonate present in the coating system. We can see the structure becomes more plastic and soft, although we are applying 2.5 Newton over here, okay, of our force of scratch hardness. Okay, so all the coating shows elastic to plastic transition before subjecting to initial crack. So A1 coating exhibit highest hardness because of small crack size as methyl groups at its interface are low interacting substitute and creating minimum interaction with indenter. So the substitution of nano calcium carbonate creates less elasticity because nanoparticles aggregation generates interactive forces, later halts movement of the polymer chain. Okay, that is what the nano calcium carbonate does as a filler. The highest filler concentration thus lowering the mobility of the polymer chain at higher filler load, and at lower filler content, the coated particles do not act as nucleation species since crystallinity is not increased. Therefore, it cannot act as a strong nucleating agent. So over here, you can see that the failure point is further in C1, C2, C3, but it becomes shorter and in C4, C5, and C6 due to the brittleness increases. Okay. So from here, we can see that the hardness, the decrease in hardness must be due to the debonding of filler particles from the matrix polymer, and the debonding of particles do not contribute to yield stress, and the filler of the coating can be indicated due to the brittleness of the coating system due to the high cross linking. Okay, so you can see the what we call the hardness. Okay, the hardness increases over here. Okay, so the hardness reduces as the composition of calcium carbonate particles increases. So on the anti-fog properties, just now before only with the binder system we see that is about 12 minutes is the best, but over here the evaporation rate with the evaporation or the condensation of water vapor on the glass becomes lesser with lesser time. Evaporation of the water vapors is lesser time with nano calcium carbonate particles. This is why we are introducing nano calcium carbonate particles, because it creates air pockets. It's confirmed it is creating air pockets where for it not to adhere with the glass and can be easily removed from the surface. Okay, so over here, this is what we see, where over here the direct coated between the cyanol species and the fog droplets over here, and this is when the nano calcium carbonate is there, when it behaves like a air pocket, it creates an air pocket over here. This is the schematic diagram, and this thing is this test has been done according to BSEN 168 test industrial standard. Okay, so what is our future work is going to be is because we are putting nanofillers into it, and agglomeration tend to take place due to the nanofillers, okay, due to the nanoparticles. Therefore, we need to have an excellent dispersing agent. And countries like Italy, they have an industry just been created only to identify dispersing agents for the coating system. So a dispersing agent is, or a surfactant is very, very important in order to disperse the nanoparticle so that it will not agglomerate and create this kind of problem. So our main research target, the next research target which we are going to go into is, we are going to use CETAP, cetrimonium bromide, which can act as an excellent dispersing agent for nanoparticles and reduces agglomeration at higher loading rate of nanoparticles. So the research work can be extended to a larger application such as PV panel, and the efficiency of coated PV panel must be compared with bare PV panel after 1 year of outdoor exposure. New and cost-effective photocatalyst materials other than TiO2, which can be incorporated into coating system for introducing the self-cleaning effect via photocatalysis process on hydrophobic surfaces, also are ongoing. Okay, so this is our photovoltaic panels, where we have also spray coated on our photovoltaic panel, and the coated panel shows a degradation rate of 1.72 after 3 weeks in service. And for BV, for a bare panel, non-coated panel, it shows a degradation rate of 5.36. Okay, this is our self-cleaning test. I want you to see the video. So this we okay, again, this we are pouring a mud. This is a mud layer. We are pouring on a bare glass and also on our coated glass surface. Okay, and you see on the coated glass, it is so hydrophobic and it is not sticking to the surface. Over here, it can be washed very easily on the coated surface compared to the bare glass, where it still has the dirt speck over here. Okay, and this is our publications which have already published. Okay, and the patent, and in fact we have also got one more patent for with nano calcium carbonate into it, and these are the competition we have already gone through, and we are already in the commercialization stage where we are bringing our product into commercialization, because self-cleaning property is one of a very important, this coating is one of a very important for anti-fog properties, and also to remove dust particles from the glass surface in building materials, in construction glass, as well as on photovoltaic panels. So thank you. So that is my card, and that is my email address and my number. Thank you so much, and the floor is open to questions.
Thank you so much, sir, for the fabulously great lecture you gave and sharing your valuable time and inspiring, informative talk. Doubt your doubt before you doubt your faith. Now the time for clarification. Sir, participants post some of their queries for clarification.
Yes.
Shall I convey the question, sir?
Yes, please.
The first one is, what are the possible applications of polysiloxane?
The one we are using is polydimethyl siloxane. And polydimethyl siloxane is basically quite expensive compared to other silicone coatings. Okay, and this polydimethyl siloxane is why we are using it in a very, very low ratio, very small ratio, so that it behaves as a binder between a glass substrate, between the glass and the nanoparticles, so that it can embed the nanoparticles into it. because it has a alkyl chain over there which can embed it through. Yes.
Next, shall I ask, sir?
Mhm.
Is there any cheaper replacement for the Silgard?
So far, we have not found anything yet other than Silgard. But even the Silgard also, it is you can use it. We are using it in a very, very small quantity, which is, I think, it is fine to be used. But rather than using an expensive brand, we can use a cheaper brand. There are cheaper brands. We can use it.
The next one is, what castable material exists that does not stick to PDMS or polyurethane elastomer?
Okay, when we are talking about polyurethane basically we use it for metal substrates. Okay, we use it for metal substrates. Okay, and this polyurethane is actually acrylic polyol with NCO inside it. That is what we call as polyurethane. Polyurethane is acrylic polyol mixed with polyamine. Okay, sorry, polyisocyanide. Okay, acrylic polyol mixed with polyisocyanide will give polyurethane, and this polyurethane is very good binder system for metal substrate. And in fact, we have also carried out the studies on that. You can check on my paper. I have already given my name card. You can Google my name in the Google Scholar. You can get the papers which we have already published using polyurethane, where we use it for anti-corrosive properties, and we introduce other nanofillers into it, and as well as other pigments into it, and we studied on the anti-corrosion properties of the using the hybrid system. Yeah.
Thank you, sir. The next one is, how long does PDMS take to cure?
Again?
How long does PDMS take to cure?
Okay. Our coating system with PDM, we use a very small amount of PDMS only. Okay, it's not a big amount of PDMS, and mostly it's ethanol. So ethanol will evaporate fast. So therefore, our coating system will get cured, tech-free time, curing within 10 to 15 minutes. It cure in ambient condition. We no need to heat treat it. Without heat treating, it can be cured within 10 to 15 minutes with PDMS Silgard into it.
Last one, sir. In which kind of industry mostly used the PDMS?
Okay, basically PDMS is widely used in glass manufacturing. Usually they use it for what we call to create a protective layer on glass. Either it can be UV to block the UV into the building. They use PDMS as the main binder to bind the filler, which can protect the transmission of UV light into the building. Okay, so usually they use it in glass panels.
Thank you, sir. Thank you so much, sir, for patiently answering the questions. Shall we move to the valedictory session, sir?
Yeah.
Okay. Now I invite Mrs. T. Meghala ma'am, Assistant Professor in Microbiology Department, to deliver a vote of thanks.
Good afternoon to all. Thankfulness is the beginning of gratitude. Gratitude is the completion of thankfulness. It is my privilege to have been asked to propose vote of thanks for today's session of International Faculty Development Program. Let me first of all start giving glory to the Almighty God for making today's occasion a resounding success. I wish to express my gratitude to our principal, Reverend Sister Dr. Eugene Amala, for providing vibrant encouragement and support. I would like to extend a special thanks to our secretary, Reverend Sister Claudine Orokia Mary, for her continued guidance. My heartfelt thanks to our administrator, Reverend Sister Andoni Amal, and Vice Principal, Reverend Sister Dr. Vimali Mary, for their unstinted support for this function. My sincere thanks to the resource person of today's session, Dr. B. Venkateshwaran, for his inspiring speech on the topic self-cleaning industrial coating. The way he explained the topic is exemplary. Please accept my deepest thanks, sir.
No, thank
I
you so much.
extend my sincere thanks to our HOD, Dr. R. Krishnaveni, who is the convener of this FDP program, for her efforts, and all the faculties of our department for their hard work and support. And I owe my special gratitude to Mr. Mahesh sir for his flawless technical support. Finally, I thank all the distinguished invitees present here, whom are professors, associate professors, assistant professors, research scholars, students of various disciplines from various colleges and universities for their cooperation in making this program a memorable success. Once again, I thank you all for your attention. Thank you.
Thank you, ma'am.